So just like when we did exponential graphs last week, alongside the left-hand side of those graphs, we had characteristics listed about its domain, range, the horizontal asymptote, the y-intercept, etc. This is similar, right? These are the characteristics of the logarithm graph. But if you were to happen to have those notes, and you don't have to get them out right now if you don't, and compare them side to side with these, what you'll notice is everything has been switched. And that's because like we talked about when we first mentioned about inverses, that you can, at its most basic form, find the inverse function by taking all the points and taking their x and y's and switching them. And so when we go to look at the shapes of log graphs, we're going to be using that feature of inverse functions to generate our new pictures. And so everything on here, I'm about to talk to as we do that. Now, if you have a printout of the notes, whether you're in class or you're at home, and you actually printed out the paper, on the second sheet or the back, there's this huge blank space in the upper right corner of the second page. We're going to fill that with the graphs. We're going to both review exponential graph because it's good to do that, especially since you have a test coming up on like, I don't know, Thursday. And then we'll use the exponential graphs to shape and form and generate our inverse function graphs for the logarithm, okay? So I want you to just divide that section up into quarters. In the left side, we're going to be reviewing exponential graphs. So label that side exponential on top. This was the y equals b to the x. And then the right side will be doing the logarithmic graphs. And that function is y equals log base b x. So the very first exponential function we did was for b greater than 0. And all the exponentials we did had 3 characteristic features that we used every time we graphed. The first one was that there was a horizontal asymptote at y equals 0. So all of them had that. There was a y-intercept at 0, 1. And we talked about that because when x is 0, you have b to the 0, and anything to the 0 power is 1. So when x is 0, y is 1. And then we talked about how when x is 1, y is equal to whatever your base is, because b to the first power is just 1. It's just b. I need to not keep getting everything mixed up. So we have 0, 1, and we have 1 comma b. And you might think, how's she going to graph 1b when she doesn't actually know what b is? Well, think about it. I just said that b, oh my goodness. Y'all, I'm messing up everywhere. If you wrote b greater than 0, because I wrote b greater than 0, erase that 0 and put 1. That was my bad. So now when we go to do the 1 comma b point, b is bigger than 1. So we're going to go right 1, and then up b is going to be somewhere above the y-intercept because that y value was 1. And so we have this basic shape. And that's our exponential growth graph. And it's always increasing on the domain because as x goes out to the right for infinity, y is also going up and increasing for infinity. So as x gets bigger, y gets bigger forever. And then here's how we're going to use that information to introduce the logarithmic function for b greater than 1. This would be our logarithmic growth graph. So remember that inverse functions, the x and the y are switched. So we're still going to have an asymptote on this one, but instead of a horizontal asymptote, we're going to have a vertical one. And instead of the line being y equals 0, we're going to have x equals 0. And that's everywhere here on the y-axis. There's my asymptote. And instead of a point at 0, 1, we're just going to flip the x and y, and we're going to have a point at 1, 0. And instead of a point at 1b, we're going to have a point at b1. And again, you might think, how's she going to graph a b value? We don't even know b. But I do know it's bigger than 1. So I have that x-intercept where I went to the right 1. And if b is bigger than 1, well, I just have to go past that somewhere. So go past that and then up 1-ish, right? We're just estimating here. And then this is the shape of that. And this is a logarithmic growth graph. As x goes to positive infinity, y goes to infinity. It's increasing everywhere on its domain. So exponential, now we have logarithmic for b greater than 1. And then the other graphs we have is, well, what does it look like when b is less than 1? So let's go back to the exponential side and review that. For b less than 1, and also we want it to be positive, so I'm going to add in greater than 0. So b greater than 0, but still less than 1. And I'm just going to write those 3 characteristics down because repetition is good for you. Horizontal axis at y equals 0. Y-intercept at 0, 1. And a point at 1b, so I'm going to go to the right 1, and then up b. b is less than 1 here, so it's got to be below my y-intercept. And that characteristic is what makes it my exponential decay shape. Because as x goes to positive infinity, y is decreasing. It's getting closer and closer to 0 without ever actually reaching 0. It gets smaller forever. Like Ant-Man. When he goes into the whatever it's called, I don't remember. And then here's how we'll use that to graph. So that's my exponential decay. So now we're going to do our logarithmic decay. So this is for b less than 1, but positive, so still it's greater than 0. It's got, instead of a horizontal asymptote, it has a vertical one. And instead of y equals 0, it's at x equals 0. Instead of a point at 0, 1, it has a point at 1, 0. And instead of a point at 1b, it has a point at b1. Now b is less than 1, so starting at 0, 0 and going to the right b distance, it's going to be somewhere between 0 and the point I already have there, because that point I already have was when b is 1. So b is less than 1, somewhere in between 0 and my x-intercept, and then just go up 1-ish. And it'll be a point right around there. And these 2 points determine my shape. Ooh, that was ugly. But you have the basic idea. That is my logarithmic decay. As x goes to infinity, y is decreasing forever. I can't just leave it like that. It was just too bad. Let me try and fix it. My attempts at fixing aren't ever really good, though. I'm just going to walk away. So here are our basic shapes. And you're welcome to just memorize all four. For me, it's better to just remember one, exponential for when b is greater than 1, and then I just kind of derive all the rest from that basic concept. But that's because I don't like memorizing a lot of stuff. If you can just understand the concepts, then you can come up with the graphs on your own, but you do you. Now we'll do some transformations, okay? And just like when we did transformations with exponential last week, I want you to come up with both the basic function and graph it, and then we're going to list the transformations, and then graph the transform function. So when you're trying to determine the basic function, remember, any plus or minuses, any negatives are not part of your basic form. Those are all modifications which we'll take care of when we apply the transformations. So when I'm asking for your basic log function, you're looking for something that's in this form, log base b of x. And so looking at this example right here, we have log base 3 x plus 1 plus 2. So this right here is your basic function, log base 3 of x. And before we talk about the transformations, let's just graph this, right? We know that we have a vertical asymptote at x equals 0. We have a point not at 0, 1, but 1, 0. And we have a point not at 1b, but b, 1. And in this particular problem, b is 3. That's our base. So you do your graph, I'll do mine, and then we'll reconvene. So there's our logarithmic growth. So then we have two transformations here, plus 1, plus 2. The plus 1 inside is a horizontal shift, so it's going to go left. And the plus 2 is a vertical shift, so it's going to go up 2. So you try that with yours, and I'll try that with mine. The left 1 makes the vertical asymptote shift to the left. And then I'm just going to take my points. My 1, 0 is going to go left 1, up 2. And my 3, 1 is going to go left 1, up 2. If you're watching this video asynchronously, I want you to pause and try it on your own. And then we're going to work it together in class, and I'll come back at the end of the video and explain what we did. Remember that when you're finding your basic function, you're not going to include any negative signs, any addition parts in your basic function. And since we're working with log, we're trying to get this in log base b of x. Well, what we have here is natural log. And what we talked about earlier in the problem, or earlier in this lesson, was that means log base e of x, where e is approximately 2.7. And I'll give you a minute to try to graph that using